Okay, this is June 2008, paper 4, question 2, and it's a question about the gas laws. In fact, this is to describe an experiment for charge law. Now, charge law is no longer on the actual specification, but again, just to go through what we need here, we have a water bath. Inside the water bath, then we have a capillary tube. The capillary tube is open at the top, but there's a little bead of sulfuric acid there, which gives us a layer of trapped air. This is inside a water bath. We also then need to have a thermometer so that we can record the temperature, and alongside this we need to have a scale so that we can measure the length of the column of trapped air. And normally speaking, in here we put in some sort of stir. So this is a water bath. Okay, so we've got a water bath, we've got a thermometer. Now whenever you're doing this, you need to make sure you use your ruler and draw that in. That's the trapped air, that's the acid thread. And we're going to heat that water bath from below, and then we've got a ruler to measure the length of the trapped air column. Then it says on figure 2.1 below, so this is this diagram here, sketch a graph of the results that would be expected. Extrapolate the best straight line through the experimental point. So, well, this is what you would expect. You would expect to get a straight line, not going through the origin. When you extrapolate that back in a straight line, it will intercept at -273, and this is the volume against temperature in degrees Celsius, which gives us a straight line which extrapolates back to -273. Okay. The ideal gas equation is given as PV equals nRT. P is the pressure, V is the volume, N is the number of moles, R is the molar gas constant, and T is the temperature in Kelvin. It then says the mole is a SI base unit of amount of substance. The definition of the mole refers to a number of particles. What is this number? Well, it's the Avogadro number. Which is 6 × 10⁻³ particles. And that is the number of elementary particles in 12 grams of carbon-12. So that's what the Avogadro number is. So that means that there's 6 × 10⁻³ elementary particles in 12 grams of carbon-12. 1 molecule of carbon dioxide contains 1 atom of carbon of mass 12U and 2 of oxygen, each of mass 16. So calculate the mass in U of 1 molecule. So it's 12U times 1 plus 16U times 2. So that's 12U plus 32U, which is equal to 44U. So that's 44U for the mass of 1 molecule of carbon dioxide. It then asks us to calculate the mass in kilograms, so that's 44 times, and then we're multiplying that by, and we look in our formula sheet and we multiply that by 1.66 times 10 to the -27, so that's 1.66 times 10 to the -27 to change it into kilograms, and that gives us, sorry, that's for 1 molecule. For 1 mole then, we need to multiply that by 6 times 10 to the 23 to get 1 mole. So this is the mass of 1 molecule, okay, of carbon dioxide, multiplied by the number of molecules to give us 1 mole, and that turns out to be then 0.044 kilograms. So 0.044 kilograms. So assuming that carbon dioxide behaves as an ideal gas, calculate the volume in meter cubed of 1 mole of carbon dioxide at a temperature. So again, we're going to use PV equal to RT. Behaves as an ideal gas, the volume in meter cubed of 1 mole of carbon dioxide. So we've got, that means that the volume then is going to be equal to nRT over P. So that's equal to 1 times 8.31 times, and the temperature is 273, divided by 1.01 times 10 to the power of 5, and that gives us a volume whenever we calculate that out at 2.25 times 10 to the minus 2. So 2.25 times 10 to the minus 2 meter cubed. Then a flexible container of carbon dioxide has a volume of 1.5 at a temperature of 25 and a pressure of 1. Calculate the mass of gas enclosed. So we're going to say that PV equal to nRT. Therefore we can say 1.15 times 10 to the power of 5 times 1.5 is equal to n times 8.31 times, and then that's 273 plus 25, so that's 298. So that means that n is equal to 1.15 times 10 to the power of 5 times 1.5 divided by 8.31 times 298. So that gives us the number of moles that we've got, which is equal to 69.6 moles, and therefore the mass is equal to, well, that's the number of moles, 69.6, and we've already worked out that the mass in kilograms of 1 mole is 0.044, so we're going to say that's equal to 69.6 times 0.044, and that gives us then a value of 3.07 kilograms. So 3.07 kilograms. So we simply use PV equal to nRT to work out the number of moles. Once we know the number of moles, we know the mass of 1 mole, therefore that gives us the mass of the number of moles that we have by multiplying by 0.044, and that gives us an answer of 3.07 kilograms.